Hello, and welcome back. This is October 15th, 2020. So I'm showing this video here to give you a short tutorial about what's going on, what's happening now this week. So just a little recap. Monday was mostly presentations. Talked about Lewis dot structures. That video is a mini lecture already posted. Tuesday, we finished up some presentations for the atomic theory timeline, and we dove into very briefly on the activity, the intro activity for naming chemical bonds and writing chemical formulas. And there were 4 pages to that. We'll look at that in a moment. And then where we left off with you was actually the same activity that I posted with the video yesterday. I posted that video yesterday, recorded that video yesterday morning. And that's what we did in class, was do those intro activities. I'm going to briefly touch on that again in a moment. And then today, this morning, over what you see here is the do now that students will be looking at today. Those students who are able to make it today, this is the do now that they will see, and so you're getting to see it yourself. So that's good news. One step closer to some sort of reality or some sort of normal for returning. So this is the this is our setup. This is our do now. You can take a look at it. Pause, take a look at the schedule, if you will. Look at the do now and think about some things, and we'll discuss that in a moment. But first, let's go back to where we left off together, and let's revisit. So in our last video, we were talking about the bonding foldable, as you see here on the slides. This bonding foldable just had us encompass and summarize all the various chemical bonds that are worthy of studying, and then the ones that we are going to be studying. This basically encapsulates every type of chemical bond. There are some other special covalents we'll look into towards the end of that. But anyway, that just gets us more specific. So we looked at this foldable. We looked at the start about filling it in. That was part of homework that's actually going to be checked today. So that needs to be updated on the do now. So we'll do that in a second as well. Ionic bonds, talked about ions, talked about properties, and then you were to get the other pieces there for the foldable and finish that. So next time I see you, make sure to show that to me so I can check it. Check you off and give you that credit as well. We looked at these in practice as well. We said this was covalent because they're all non-metals involved, or we would say there's only right side of the periodic table elements. Hydrogen is the exception to that rule, but we just treat it like a right-sider because it's not a metal. So in that tool, using the tool of left side, right side, metal, non-metal. This one is clearly a metal, non-metal. Even though aluminum is kind of a metalloid, it acts mostly like a metal than anything else. And in terms of calling it ionic, covalent, metallic, treating metalloids on the left side like metals and treating metalloids on the right side like non-metals is safe. Copper was metallic, platinum was metallic. Magnesium chloride, you got a left sider in magnesium and a right sider in chlorine. Metal, non-metal, i.e. ionic, and covalent, because 2 non-metals. We've gotten to that bonding inquiry activity, and you guys are as well. I'm going to look through that with you in a moment. Similarly as to how I would go through those rules that were gleaned from the in-class activity. I'll be doing that right after the do now, because the do now kind of guides them through that thought process again, kind of reminds them about what they did in the lab. We're going to do that right this minute in the video, and I'm just going to briefly summarize the rules you should have gleaned. Now, I will say right now, if you have not looked at that worksheet yet, the one that I'm about to show you, the bonding inquiry activity, and you haven't tried it yourself on your own paper to try to write some things down as it instructs you to do, please pause. Don't go further yet. Don't look at it first. It's a better tool for you to use if you can physically try it yourself and then go back and listen to this. So please pause right now if you have not done it already, because I'm about to go through it. And you need to have done it on your own for the genuine learning of it. I promise it'll be easier and better for you to have learned it in total to do it this way. Please, please, please do that just for me. So, as promised, hopefully you've practiced this on your own. Activity 1, the students did it in groups, in their color groups, and I just kind of wandered around and kind of would poke and prod and hints, just verify some of the thoughts that they were having as they saw it. But if you look at the patterns here, first thing you notice is their chemical formulas, so show the symbols next to, very close to, other symbols. It represents the formula of a chemical compound, okay, or chemical bond. Then we have here, the written form takes the metal first element, or the metal, writes its name down. And the second element, this is where the things is worth noting, is the second element ends in "ide" every time. That second element is a non-metal. So the first rule here is that a chemical formula is written by saying the metal, then writing or saying the non-metal with a new ending, an "ide" ending. Some ones are a little bit more tricky, but not huge trickiness. It kind of makes more sense. Like bromide just drops off the "ene," the "ine," and makes it "ide." If that makes sense. But then phosphorus is like, where do you cut it off? Why isn't it phosphoride? Why is it phosphide? Scientists somehow thought that getting away with making it shorter would just be a better shortcut, make it better in general, clearer. Same thing goes with sulfur. We don't call it sulfuride, we call it sulfide. So similar reactions there. Fluoride, oxide, instead of oxygenide, it's oxide. Or nitrogenide, it's nitride. They just seem to flow a little bit better. Try to cut out as many syllables as possible from that. So anyway, you see that the name has a metal and a non-metal. The non-metal's ending is "ide." It's one rule. The other rule is that you write the formula by taking the symbols, going ahead and writing them down is a good thing. And then there are subscripts that are based on what each element brings to the formula in terms of its in terms of its oxidation number. Get that oxidation number from the periodic table first. The ones I gave you in your rainbow packs show it. It's at the very top of those columns, +1, +2, or 2, 1, 2, 1 plus, or 2 plus, 3 plus. Those oxidation numbers tell you what that element brings. Now you notice there are no pluses and minuses in the subscripts, so the pluses and minuses don't carry over into this. Pluses and minuses you do not write in the subscript, nor do you write it anywhere in the formula. So just remember that. So a little key nuance is that in the chemical formulas, we don't write pluses and minuses, but we worry about the oxidation numbers for what we will write as the subscript. So if we explore this, and I asked and poked and prodded, said, where did the 2 come from in CaF2? Well, in the theory format, we say that calcium would like to give up 2 electrons. Fluorine comes to that compound wanting to take 1 electron. So if 1 fluorine comes in bonds with calcium, that takes 1 of calcium's electrons away that it wants to give. Fluorine satisfied, calcium is partially satisfied because it gave away 1 electron. But calcium still has another electron to give away, so it needs another fluorine. The other fluorine I'm going to use is this pin. The other fluorine, this pin, satisfies the other need to give away another electron by calcium. And so there's 2 fluorines needed for 1 calcium. It just happens to work. It just works out that way. Very fortuitously, helpfully, and it just works. But that's the theory. In practice, we say, what does calcium bring in terms of its oxidation number? And I might end up showing this backwards because I want to make sure I show it to you the way you would see it. So calcium on the left side for you brings 2 plus to the chemical bond. Fluorine is a 1 minus oxidation number. So then what happens is those oxidation numbers, we don't worry about their signs, will swap places to give us the subscript. So that it's calcium 1 when you don't write a subscript at all. That just means it's an understood 1. Just like saying X is the same as 1X. Just think about that. And then it's F2. There's 2 Fs. So calcium brought the 2. Fluorine brought the 1. And they swap places to form the subscript. Ca1 or CaF2. You get it? You'll see a lot more. Look at the next one, K2, K2O. K brings a 1. O brings a 2. Crisscross or swap. And you say K2O1. You see that? Magnesium's even easier. Magnesium, I want to do it on my left side, but I'm going to try to do it to yours. Magnesium brings a 2 because it's in the 2 plus column. Nitrogen brings a 3. Verify. Pause and verify with your rainbow pack if you need to. Then those oxidation numbers brought magnesium brought a 2, nitrogen brought a 3. Swap, and that becomes our subscripts. So that we would say Mg3, nitrogen 2, even though the 3 came from the nitrogen. So continuing along, the patterns you'd see are the subscripts have something to do with oxidation numbers. The ides are the endings of the nonmetals. There's a metal name involved. There's a nonmetal. Those are what you observe. The rules you would write are that you write the metal, then write the nonmetal, change the ending of the nonmetal to ide. The formula is you look at what each element brings in terms of its oxidation number, get rid of the signs, swap them, and then you write the formula with those subscripts of swapped oxidation numbers. Now, what happens if you have the oxidation numbers are the same, like aluminum brings 3 and phosphorus brings 3, so that when they swap, you can reduce it like a fraction, right? Like 3 over 3 reduces to 1 over 1. So 3 subscript reduces to 1 and 1. So that's why it's just written as ALP, because those understood 1 subscripts. Go back and listen to that. That was catchy. This was the longest one to come up with rules. The other ones kind of flowed a little bit faster, but they had some other nuances to it. So that last rule was look at the oxidation numbers that each element brings, crisscross them or swap them to write them as subscripts, ignoring the signs. Ignoring the signs, big deal. So then you would practice these. We'll give you a couple of them. CaCl2, MgS, because the subscript's reduced, Li3P, Rb2Se, Al2O3, and you can do some of the other ones and show them to me later. Strontium chloride, this would be called strontium chloride, practicing naming. Barium oxide, cesium nitride, calcium selenide. Those are easier to do, to go from formulas to names. The next one had you look at variably charged cations. So basically this one was, what happens if I can't find the oxidation number on the front of the periodic table? Well, on the back left side shows you elements that have what's called multiple oxidation states. Okay, oxidation states just means oxidation numbers, right? It's the number that's over most of the columns on the periodic table, some of the columns. There are some elements like transition metals and ones in the carbon group that don't have oxidation numbers provided over the column. You can't get it from the front of the periodic table. As a persistent student, it should be, well, where can I find them? Let's just flip the page over. Let's flip the Rainbow Pack periodic table over and look at what is on the back side. And on the back side are some various other oxidation numbers that we'll look at. So I'll show you right here. We've got the right side, other side. Right there, we've got several metals. Oxidation states, there's multiple. Notice copper right there has copper 1 and copper 2. And what does that mean? It means, look, find copper on the front there. Copper. It does not have an oxidation state above its column. Oh no, what do we do? Well, we flip it over on the back and we look at what its possibilities are. So it just tells you what it is. Also, we can see that, the oxidation states can be provided to us here by the Roman numerals. So the big rule here on the page is that from this page, we notice that there are Roman numerals, and the Roman numerals match up to what is swapped. That swappable oxidation number. So the Roman numeral is probably the oxidation number. You still have the ide endings. All the other rules still exist. It's just the new rule is oxidation number of the metals can be provided by the Roman numerals, and vice versa. We should be able to get the Roman numerals or deduce the Roman numerals from unswapping. So before we took our oxidation numbers and we swapped, wrote them as subscript, we should be able to unswap, and then it won't necessarily be exactly that every time. We have to do some deduction. I'll show you what that means in a minute for some of these. Because look at lead sulfide, for example. If I unswap PB and S subscripts, that's going to be PB brings a 1 and S brings a 1. But wait a minute. I have to ask myself, first of all, when I unswap, does that lead to a legal setup? Well, first of all, the written form's given to me. It says lead 2. That's not what unswapping leads to. Unswapping PB1, S1, gives us PB has a 1 plus and S has a 1 minus, just from unswapping. If we take those subscripts and they're swapped and unswap them, we would say, from the unswapping, we would say PB brings a 1, S brings a 1. So that should be lead 1 if unswapping works. But unswapping is not reliable. What is reliable is the deduction. So we say, all right, the best thing is to look at the not know first. Does sulfur really bring a 1? Turns out, no. Sulfur brings a 2. Sulfur's in the oxygen column. Sulfur brings a -2. So if sulfur brings a -2, then why isn't there a 2 next to PB? Because PB must have also brought a 2, so that when they swapped, they would reduce to 1 and give us PBS. You follow that? If not, go listen to that part again, because I would just re-explain it to you again that way anyway, and we can clear that up. But notice, PB, we just look at the subscripts. Best thing to look at how to write the name is to actually look at the nonmetal, find its charge, and then see how that works in the formula. So for this again, PBS, I see that PB or S would bring a -2 charge, and PB, let's just see what it would be. If S brought a -2 charge and it swapped down, that would mean PB should have a PB2. Since it does not, PB must have also brought a 2. So PB must have gotten the 2. PB lead has a 2, and that's where I write the Roman numeral. Why do I say that? Because down here on the practice, I ask for formulas, and you have to write the names. You have to know what Roman numeral to write the name for, right? You're not always given the Roman numeral. You are given some direction though, because on this back side here, it actually shows what some of the possibilities are. It's not an exhaustive list. There are some out there in the world that do exist that are not on my list. These are the ones we'll use going forward past this day, but just understand that that's a list of most of the possibilities and all the possibilities that we'll use in this course. Anyway, so for example, PBS right here, that would be lead 2 sulfide, because sulfide brings a 2. So lead must have brought a 2, because when they swapped, they reduced it to 1, PBS. That's different for PbO2, another tricky one. We know, if we start with the nonmetal, we know O brings a 2 minus to the table, because it's above the column. Oxygen's column is a -2 column. So if PB brought a 2 and they crisscross, it should just be PbO. So PB must not have brought a 2. And there's no 2 next to PB. But oxygen only brings a 2. So it's got to be oxygen brings a 2. PB must have brought, if we look at our possibilities, a 4. Crisscross down. So it should be PB2O4. But wait, those numbers reduce. 2 over 4 reduces to 1 over 2. So PB1O2. Same thing's true with CuSe. Copper selenide. Selenium brings a 2. Copper would have to bring a 2, because when they swap, they can reduce and be Cu1Se1. Cool? Good. The last one was, the last rule here was on ionic compounds. The big thing to notice is look at like NH4 here. By the way, when it says plus, that really just means 1 plus. It's no different. I'm going to go ahead and fix those though, because this becomes ever the bugaboo in the future. Notice this is not C2H3O2 and the 2 is minus. No. This is all one entity. Let me just finish these first, and I'll get back to that. Okay, so the big thing to look at here is that NH4, as it appears down here, is parenthetical. Big rule is these polyatomic, that just means many atoms. So nitrogen and 4 hydrogens, that's more than one. So many polyatomic, many atoms. in the ion. It's a single one ion with multiple atoms in it. It acts like one ion, just like potassium is one ion, K plus. NH4 is one ion with one charge that it brings to the table, one oxidation number that it brings to the compound. How we make it act like one is we use parentheses. And overuse of parentheses will never lead to a penalty. I shouldn't say never, because there could be way overuse of a penalty. Of parentheses. But anyway, what you see here is that we use parentheses around NH4 so that the subscript does not alter anything of the formula. The formula needs to be NH4 because NH4 is NH4 is NH4 is NH4. It's ammonium. It's called ammonium. It's always NH4. It's always NH4. And it needs to be totally and always only NH4. So we use parentheses to protect that it's NH4, its identity. And then if a subscript comes along, it goes outside the parentheses like we see this 2 comes along here. So just like normal, NH4 brings a 1 plus. To your right side, yep. Sulfur brings a 2 minus. Crisscross down. Wait, no, I've got it like me. NH4 brings a 1. Sulfur brings a 2. Yeah, because it would be your left and right. Crisscross down. That's NH4 2 out on the outside of its parentheses with a 1 next to S. You follow that? My hands may be backwards, but just follow that I'm saying what the formula is. The 2 came from sulfur, brought to the compound, goes to the entire new ion, the entire ion there, positive ion, and becomes its subscript. We do it only to its subscript, so it becomes outside the parentheses. The parentheses separate. So what we would notice as our observation list here is, patterns we observe is that the entire ion is parenthetical. But one other key point is that it's only parenthetical when a subscript is needed. Let's look over at COSO4. So cobalt, we would find from the back of the periodic table, is cobalt 2. Cobalt 2 brings a 2 to the table. Sulfate brings a 2 minus to the table. Now that's listed up here, sulfate. But it's also listed on the rest of the back of your periodic table. Right. There. Sulfate. Notice there's also a sulfite, and that compares to sulfide. Sulfide comes from the front of the periodic table. Sulfate and sulfite come from the back. So that becomes like another reference point for how to find what that ion brings to the table. So we would say in this case, cobalt sulfate. Cobalt we find from the back side also brings a 2, or could bring a 2. We'd just test it first. We'd say it brings a 2, and that sulfate brings a 2. And they crisscross down, or you may have seen beforehand, those 2's can reduce because 2 over 2 is reduced to 1 over 1 of the fraction. Subscripts do the same thing as fractions in reduction. So we write CO with a 1, or don't write the 1 because subscript 1 you don't have to write. SO4, and we could put parentheses in. We could make this like this. We could make it like that. And that wouldn't be wrong, but just in standard format, if there's no subscript to write because it's an understood 1, you don't need parentheses. So if you don't have to write the 1 subscript, you don't have to write the parentheses. Just know that. But if you do write the parentheses, you won't be counted off. It's still legal to do. It's just not the standard format, so you won't see it that way. If you were to see one on the test and I said, here's the formula right here, give me its name, you would need to say cobalt, find its oxidation number from the back, sulfate from the back, so I'd name it cobalt 2 sulfate because that's what yields this same formula. If I tried cobalt 3, it would not yield this formula. It yields CO2SO4 with parentheses and 3 on the outside. Try writing that and see what I mean. If it were cobalt 3, that's another possibility from the back of the periodic table. Anyway, you can run through some of the other ones and see how those formats exist and work out. The rule is that a polyatomic ion acts like one ion, and we show that with parentheses as often as we need to. Technically, you don't need them if we don't have a subscript. So I have you practice writing these. So this would be Fe, and then acetate brings a 1. So Fe iron brings a 3. Acetate C2H3O2 on the back of your periodic table here. Very top, acetate brings a 1. They crisscross down, and you get Fe parentheses C2H3O2 close parentheses with a 3 on the outside of parentheses. Write that, and then I can check it later if you want me to. You can send me a picture and be like, is this what you meant from that video? And I'll tell you yes if that's what you put. Same thing goes with some of these other ones. You write the names, though. Big thing is that for like metals like copper, zinc, tin, lead, nickel, you need to find the oxidation number and write the Roman numeral. Get that from the back. Activity 4 had us do covalent naming bonds, and we just noticed that there are prefixes that tell you the subscript. Now this is different because it was that the Roman numerals were next to the whatever it was were what swapped, right? We said like iron 3 meant it brings 3 to the table and then swaps down and becomes a subscript of the other thing. Now we say in covalent that the prefix indicates the subscript of that element. So trifluoride means F3, right? Dinitrogen means N2. Mono means oxygen, oxide. So the way it goes is mono is 1, di, tri, tetra, penta, hexa, septa, octa, nona. And then there's deca as well. That'd be 10. So deca, undecam, duodecam, that'd be 12. And then as we get more complicated, there's actually a whole other naming system for those types of covalent bonds. This one's way easier. Big thing is you got prefix tell you the subscripts. Subscripts tell you the prefixes. That's the reverse of that rule. And that becomes the rule, pretty much the same as what you observe. And predicting these are pretty straightforward because they are just that. That would have concluded then the end of the bonding activity. And that would have brought us to the end of this slide, and then we would continue through the slides. And I'm going to encourage you to do that. Today in class, we're going to go through these slides. Once again, these slides are in your class docs folder. In the bonding section on Google Drive, Night Chemistry class docs folder, in bonding, class notes. I think it's version 1.0 there. And we're just going to run through these notes the rest of the way. We have a kinesthetic bonding activity that comes along, and it guides you through it. You technically don't need the kinesthetic pieces, but we'll have them. I can show you those at a later date. I'm not going to live stream today. This is it. This is a little bit longer video, but I want you to go through these slides first, and then tomorrow we'll recap where we went through, go through these slides that go through predicting ionic charges and whatnot, and you will be good to go. So thanks for joining us again today. Thanks for being diligent and focusing, and I hope to see you soon. Please hurry back, feel better, and we'll see you back in here. Here's a look around the room, just in case you're wondering. Hasn't changed much. So, go Dogs.